In this example, we have the favorite agricultural firm which makes profit from selling two products, cotton and corn. Both products face these inverse linear demands, where X is in tons of cotton and Y is in dozen bushels of corn. We also have the cost of production. Our tasks are to set the profit function, find the combination of cotton and corn that maximizes profit, and check that the point is a relative maximum. We also will need to calculate the maximum profit and to provide the prices for X and Y. First, let's compute the profit function, which is equals to the revenue obtained from selling cotton and from selling corn minus the cost of production. So the profit in terms of quantities is equals to, here we can replace the price as a function of quantity using the inverse linear demand. We can do the same thing for the case of the price of Y. Minus the cost of production, which was x squared plus y squared plus 6xy. And now we can use algebra to reduce these operations. So this is 56x minus 4x squared plus 48y minus 2y squared minus x squared minus y squared minus 6xy. This means that our profit function will be equals to 56x, and then we have minus 4 minus 1, so this will be minus 5x squared plus 48y, and then minus 2 minus 1 is minus 3y squared minus 6xy. So this is our profit function. Our second step is to find our optimal combination of cotton and corn that maximizes profit. And we do that by using the first order condition. First, we take the derivative of the profit with respect to x. So here we have 56, then the derivative of 5x squared is 10x. These two terms, when we take the derivative with respect to x, is 0 because they do not contain x. Minus, here the variable part is only x, remember. So the constant part will be 6y times the derivative of x with respect to x is 1. So 1 times 6y is 6y. And we set this partial derivative equals to 0 in the first order condition. Let's do the same, but now with respect to y. Remember, when we take the partial derivative with respect to y, x becomes a constant. So here the first two terms, the derivative is 0 because they do not contain y. Then we have here derivative of 48y with respect to y is 48 minus, here we have 6y minus, notice that now the constant part is 6x. And then the derivative of y with respect to y is 1. So 1 times 6x is 6x. Now from here, notice something interesting. So we can put 56 minus 10x equals to 6y. And we can replace that function here. So this is 48. And instead of putting 6y, we can just write 56 minus 10x minus 6x equals 0. So this is 48 minus 56 plus 10x minus 6x equals 0. So this is 4x equals 48 minus 56 is minus 8. We move it to the right hand side as positive 8, which means that x is equals to 2. Now let's solve for y. So this is 56 minus 10 times 2 equals 6y. So this is 56 minus 20 is 36 divided by 6, y is equals to 6. So this means that our optimal values are 2 for cotton and 6 for corn. Our next step is to verify that our critical point is a relative maximum. And remember that in order to ensure that, we need to satisfy the three requirements, in which the second partial derivative with respect to x and with respect to y both has to be less than 0, and then the multiplication of both has to be greater than the cross partial derivative square. So here we need first the second partial derivative with respect to x, and this can be found by taking the partial derivative of pi x, which we found in the first order condition. So here we have that the derivative of 56 with respect to x is 0. Then the derivative of minus 10x with respect to x is simply minus 10. And then the derivative of minus 6y with respect to x is 0. So this is minus 10. And because this is less than 0, our first condition is satisfied. Now let's continue with the second partial derivative with respect to y. This is the derivative of pi y with respect to y. So again, the derivative of 48 with respect to y is 0. The derivative of minus 6y with respect to y is minus 6, and the derivative of minus 6x with respect to y is 0. So we only obtain minus 6 from here. And this is also less than 0, so our second condition is satisfied. Now we need the cross partial. The cross partial, we can obtain it as the derivative of pi x with respect to y. Here, the first two terms do not contain y, so the derivative is 0. And then the derivative of minus 6y with respect to y is minus 6. And now, let's multiply pi xx times pi yy. So this is minus 10 times minus 6, this is 60. And then on the other hand, we need to square the cross partial. So this is minus 6 squared, which is 36. Because 60 is greater than 36, then our Hessian requirement is satisfied. And as you can see, we have the three requirements satisfied, which ensures that our point is a relative maximum. In our last step, we need to find the prices for X and Y and the optimal profit. So first, let's start with the prices. Recall that we have already the inverse linear demands as function of quantities. So for the case of X, the price of X is simply 56 minus 4 times the optimal quantity, which is equals to 2. So this is equals to 56 minus 8 is 48. So this is the price for cotton. Then for the case of corn, this is 48 minus 2y, and the optimal y was equals to 6. So this is 48 minus 12 is 36. So this is the price of corn in dozen bushels. And finally, in order to obtain the optimal profit, we just need to plug the values obtained as critical points for cotton and corn. So here we have 56 times, in this case, the optimal X was equals to 2 minus 5 times 2 squared plus 48 times the optimal Y, which is 6, minus 3 times 6 squared minus 6 times X, which is 2, and Y, that is 6. When you solve that algebra, you obtain that your optimal profit is equals to 180. So this is the solution of our problem.